The cold arrived during the pre-dawn hours of January 14, moving into the city from the northwest with sustained wind speeds that exceeded 30 miles per hour and ambient temperatures that stabilized near 7 degrees Fahrenheit by the time the first residents attempted to leave for work. This represented the fourth consecutive night below 15 degrees, a duration that placed mechanical components in building entry systems beyond their tested operational range, not through intensity, but through cumulative exposure. Electronic strike plates in residential building doors typically carried temperature ratings between -4 and 122 degrees Fahrenheit, specifications derived from controlled laboratory conditions rather than prolonged field deployment in wind-exposed vestibules, where radiant losses and air infiltration created microenvironments substantially colder than reported citywide readings. The buildings themselves remained structurally sound and fully powered, with heating systems functioning within normal parameters and internal temperatures holding steady between 68 and 72 degrees in occupied units. What began to fail was not the infrastructure supporting habitation, but the specific mechanisms governing transition between interior and exterior zones. The magnetic locks, electronically controlled deadbolts, motorized strike releases, and RFID card readers that managed access at entry points. These components operated in threshold spaces where building envelopes met exterior conditions, locations where architectural drawings showed weather protection, but where actual installations placed sensitive electronics in partially exposed alcoves, recessed door frames, and vestibule chambers that channeled wind directly across circuit boards and actuator assemblies. The duration of cold exposure mattered more than minimum temperature because lubricants in mechanical components gradually increased in viscosity, solder joints underwent repeated thermal contraction cycles, and battery backup systems in access control panels depleted faster than their specified discharge rates. Building management systems logged no critical alerts during the early morning hours because monitored parameters, HVAC operation, electrical distribution, fire safety systems remained within acceptable ranges, while the access control network operated on separate infrastructure that reported operational status based on whether devices responded to polls rather than whether they could physically complete their designed functions.
The first access failures appeared as isolated incidents between 6 and 7 a.m., distributed across multiple building types and manufacturer systems in a pattern that suggested environmental cause rather than targeted malfunction. A resident in a Midtown East high-rise approached the building entrance at 6:12 a.m., presented her access card to the reader, received the expected confirmation tone and LED indication, but found the door mechanism unresponsive when she pulled the handle. The electromagnetic lock had released electronically, but the spring-loaded bolt had not retracted due to increased friction in the striker assembly at temperatures near 5 degrees Fahrenheit. She attempted the sequence 3 additional times over 90 seconds before a departing resident opened the door from inside, allowing exit through coincidental timing rather than system function. Similar events occurred at buildings in Murray Hill, the Upper West Side, and Long Island City within the same hour, each involving access control systems that acknowledged credentials correctly but could not complete mechanical actuation. Building superintendents received calls reporting door malfunctions beginning at 6:45 a.m. and in most cases interpreted the complaints as isolated equipment failures affecting individual entry points rather than systematic degradation across the building's access network. Troubleshooting followed standard protocols, checking whether the affected door's power supply showed correct voltage, verifying network connectivity to the access control panel, testing whether manual override keys could bypass the electronic system. These diagnostics confirmed that electrical systems remained operational, but they could not measure the physical state of actuator mechanisms or the degraded performance of mechanical components operating beyond their cold weather tolerance thresholds. Maintenance staff applied penetrating lubricant to several jammed strike plates and reported the incidents resolved, not recognizing that the lubricant itself would thicken within minutes of re-exposure to sub-freezing temperatures. The distributed nature of these early failures prevented pattern recognition because each building's management operated independently, and the access control system vendors received no aggregated failure reports that would have indicated a weather-related degradation event affecting installations citywide.
Between 7:30 and 9 a.m., the volume of access-related incidents increased across residential buildings in proportion to resident departure activity during morning commute hours, with failure modes expanding beyond stuck strike mechanisms to include RFID reader malfunctions, keypad entry errors, and complete door controller lockouts. Card readers mounted in exterior wall recesses experienced condensation formation as warm, humid air from building interiors contacted sub-freezing reader housings, creating moisture films on antenna circuits that disrupted RF coupling between cards and readers, even when both components remained electronically functional. Residents presented valid credentials repeatedly, observing the reader's indicator lights but receiving no access grant signal because the electromagnetic field strength had degraded below the threshold required for reliable card detection. Numeric keypads suffered different failure mechanisms as plastic key surfaces contracted differentially from the underlying contact switches, creating misalignment that caused button presses to register incorrectly or not at all. A resident entering a 4-digit code might successfully input the first 3 digits before the 4th key failed to make contact, resulting in an invalid code error and a 30-second lockout period before retry. Door controller units installed in unheated vestibule cabinets began experiencing processor lockups as operating temperatures approached the lower limits of their industrial temperature ratings, typically specified as negative 40 degrees Celsius, but dependent on stable voltage supply and minimal thermal cycling. The combination of sustained cold and voltage fluctuations from heating system loads caused several controllers to enter fault states that required manual power cycling to restore operation, a procedure that building staff could only perform after identifying which specific controller had failed within a distributed access control network that might include 20 to 40 separate units throughout a large residential building. Residents attempting to exit buildings encountered the same mechanisms in reverse. Interior-mounted request-to-exit sensors functioned correctly, but the strike-release mechanisms in door frames did not respond with sufficient speed or force to allow passage, creating situations where residents could activate the exit request but could not physically open the door within the standard 3-second release window. The operational margin within building access systems derived from the assumption that mechanical and electronic components would function across their rated temperature ranges, but would not be required to operate continuously at the extreme limits of those ranges while simultaneously subjected to wind-driven convective heat loss and repeated thermal shock from door opening cycles. By mid-morning, these assumptions had been exceeded across hundreds of building entry points as the sustained cold exposure created conditions that fell outside the design envelope used during system specification and installation. Access control integrators typically selected components based on manufacturer data sheets that provided temperature ratings, but these ratings represented laboratory-determined operational limits rather than field performance under combined environmental stressors. A magnetic lock rated for negative 20 degrees Celsius might function reliably at that temperature in still air with stable power supply and no mechanical loading, but the same lock installed in a building entrance experienced wind chill effects, voltage sag from building electrical loads, and mechanical stress from doors that had expanded or contracted beyond their frame clearances. The compounding of these factors meant that actual failure thresholds occurred at temperatures significantly warmer than rated minimums, and the duration of exposure determined whether components could recover normal operation during brief warming periods or had degraded beyond their ability to self-recover. Building entry doors in New York residential construction typically included weather stripping and vestibule designs intended to minimize heat loss, but these provisions protected the building's thermal envelope rather than the access control hardware, which remained exposed to exterior conditions in order to function as an entry control point. The gap between protective intent in architectural design and actual environmental exposure of electronic components represented a specification oversight that became apparent only during extended cold weather events that pushed systems beyond their tested resilience. Between 10 a.m. and 12 p.m., building management companies began recognizing that access issues represented systematic failures rather than isolated equipment malfunctions, as call volumes to maintenance staff exceeded normal daily totals, and multiple entry points within the same buildings reported similar symptoms. The failures had progressed beyond inconvenience to functional impairment. Residents who had left for work in the early morning and returned during midday for forgotten items found themselves unable to re-enter buildings, while residents who had delayed departure waited inside vestibules, repeatedly attempting to activate exit mechanisms that responded intermittently or not at all. Building staff responded by propping doors open with physical wedges or by placing door controllers in permanent unlock mode, decisions that prioritized access over security because the alternative was residents unable to enter or exit their homes. This shift from controlled access to open access occurred building by building as management staff made local decisions without coordination or guidance from the access control system vendors, who were receiving service calls but had not yet issued technical bulletins acknowledging a cold weather vulnerability in their installed base. The transition to manually overridden access created new operational problems because building staff had to maintain physical presence at entry points to monitor who entered and exited, drawing personnel away from other maintenance responsibilities and creating coverage gaps at buildings where single superintendents managed multiple entry points. Some buildings attempted to maintain electronic access control by having maintenance staff stationed near malfunctioning entry points to manually unlock doors when residents approached, but this solution proved unsustainable as staff could not maintain continuous coverage throughout the day. The documentation of these failures remained fragmented across individual building management systems, incident logs, and maintenance work orders, with no central collection point that would have allowed analysis of failure patterns or recognition that thousands of residents across the city were experiencing similar access issues during the same time window. The afternoon period between 12 and 3 p.m. represented peak system stress as ambient temperatures remained near their daily minimum despite solar radiation, and buildings operated with entry points in various states of manual override, partial function, or complete failure. Access control networks in residential buildings typically operated as distributed systems, with local door controllers communicating through network infrastructure to central management servers that logged events and maintained resident credential databases. But this architecture meant that failures cascaded through multiple layers. A door controller lockup prevented communication with the central server, creating the appearance of network failure when the actual problem was localized hardware malfunction from cold exposure. Building management staff attempting to diagnose issues found themselves troubleshooting network connectivity, resetting controllers, and testing individual components, while the underlying environmental cause continued to degrade system performance faster than repairs could restore it. The standard approach to access control maintenance assumed that component failures occurred randomly and independently, allowing repair or replacement of individual units to restore system operation. But during this event, failures occurred simultaneously across multiple entry points and affected similar components in similar ways, overwhelming the repair capacity of building maintenance staff, who were trained to address isolated equipment problems rather than systematic environmental degradation. Some buildings contacted their access control system integrators for emergency service, but integrator response times ranged from several hours to next-day appointments because the volume of service requests exceeded available technician capacity and because the cold weather itself created access and transportation difficulties for service personnel. The integrators who did respond during the afternoon hours found themselves cycling power to door controllers, warming electronic components with heat guns, and applying lubricants to mechanical assemblies, measures that provided temporary relief but did not address the continued exposure to conditions beyond design specifications that would cause failures to recur within hours. By 3 p.m., the event had developed characteristics that distinguished it from typical equipment failure patterns. The failures were widespread but not universal. They affected similar components across different manufacturers and installation dates. They showed partial recovery during brief warming periods before degrading again, and they persisted despite standard troubleshooting and repair procedures. Building management staff documented these observations in work orders and incident reports without recognizing their significance for understanding the systematic nature of the access degradation. A building superintendent in Astoria noted that the lobby door strike mechanism had failed, been repaired, and failed again within 2 hours, suggesting that the repair had not addressed the root cause. A maintenance worker in Chelsea observed that access card readers on the building's south-facing entrance worked normally, while readers on the north entrance failed repeatedly, indicating that solar heating on the south face raised component temperatures above the failure threshold, while shaded north-facing components remained too cold for reliable operation. A property manager in the financial district logged that residents had reported access problems throughout the day, but that the building's access control server showed no error conditions, revealing the gap between actual mechanical function and monitored system status. These distributed observations remained isolated within their respective building management contexts and were not aggregated or analyzed for common patterns that would have indicated an environmental cause affecting the operational margins of access control systems. The lack of systematic data collection and analysis reflected the organizational structure of residential building management in New York, where individual buildings operated under separate ownership and management companies with no mechanism for sharing operational intelligence or coordinating response to events that affected multiple properties simultaneously. The period between 3 and 6 p.m. saw continued access control degradation as temperatures remained below 10 degrees and wind speeds sustained through the afternoon, preventing any thermal recovery that might have restored component function through natural warming. Building staff had by this point implemented various workaround strategies. Some buildings maintained doors in unlocked mode with staff supervision. Others had residents coordinate entry and exit through specific time windows when staff could manually operate access points. And some had reverted to physical key access for residents willing to retrieve backup keys from building management offices. These adaptations allowed continued building access, but it significantly reduced operational efficiency and with complete abandonment of the electronic access control and audit trail capabilities that the systems had been installed to provide. The shift to manual operations revealed dependencies that had been obscured by normally functioning electronic systems. Building staff needed to maintain current resident lists to verify identities when electronic credential verification was unavailable. They needed physical access to door controller cabinets to perform manual resets, and they needed communication protocols to coordinate access across multiple entry points when electronic notification systems could not reliably report door status. The number of residents affected by access issues during the day could not be accurately determined because most incidents were resolved through informal workarounds that generated no formal documentation, and because residents who encountered access problems often attributed them to user error or temporary glitches, rather than recognizing them as symptoms of systematic failure. Building management companies did not compile incident statistics or attempt to estimate the scope of access disruption across their property portfolios because their operational focus remained on resolving immediate access problems at individual buildings rather than analyzing patterns across multiple properties. As evening approached and temperatures began a gradual rise toward 12 degrees Fahrenheit, some access control components showed functional recovery, while others remained degraded or inoperative, creating inconsistent system behavior that proved more difficult to manage than complete failure would have been. A door controller that had been locked up during afternoon cold exposure might recover normal operation as evening temperatures rose, then fail again during overnight cooling, creating an access pattern that appeared random to residents and maintenance staff who lacked visibility into the thermal cycling of component performance. Card readers that had failed due to condensation began functioning again as moisture evaporated, but the improvement was temporary because subsequent door openings introduced new humid air that would condense on cold reader surfaces during the next thermal cycle. Strike mechanisms that had jammed during peak cold exposure sometimes freed themselves as metal components expanded slightly with temperature increase, but the accumulated stress from repeated jamming had in some cases bent striker plates or damaged spring assemblies in ways that would cause continued malfunction even after temperatures normalized. The intermittent nature of these failures made systematic diagnosis difficult because maintenance staff testing components during brief functional periods would find them operating correctly, only to have residents report renewed failures minutes or hours later when conditions changed. Building management documentation from the evening hours reflected this confusion, with work orders noting that problems had been resolved or could not be reproduced, despite residents reporting ongoing access difficulties. The gap between component testing under controlled conditions and actual performance under variable environmental stress revealed a fundamental challenge in maintaining building systems that operated at the interface between interior and exterior environments, where conditions could shift rapidly, and where design assumptions about environmental stability did not hold.
Documentation review conducted in the following weeks by building management companies, access control system vendors, and property insurance carriers revealed that the access disruption event had affected an estimated 4,000 residential building entry points across the 5 boroughs, though the actual number remained uncertain due to incomplete incident reporting and the tendency to classify access problems as routine maintenance issues rather than systematic failures. Internal reports from access control manufacturers acknowledged that sustained operation below 15 degrees Fahrenheit for periods exceeding 12 hours represented conditions beyond the validated performance envelope for many installed components, particularly in applications where devices were mounted in partially exposed locations subject to wind chill and thermal cycling. The manufacturer's operational temperature specifications had been based on steady-state laboratory testing that did not adequately represent field conditions during extended cold weather events, and the installation practices used by system integrators had prioritized network connectivity and electrical protection over thermal protection of sensitive components. Building code requirements for access control systems addressed fire safety integration, fail-safe operation during power outages, and accessibility compliance, but did not specify environmental performance standards or require validation that systems could maintain function during extreme weather conditions within the local climate range. Planning documents for building management operations included procedures for responding to power failures, elevator entrapments, and fire alarm activations, but contained no protocols for managing systematic access control failures or for maintaining building entry when electronic systems degraded. The event timelines reconstructed from building automation system logs, access control event databases, and maintenance work orders showed that failures began during early morning cold exposure, peaked during midday when temperatures reached minimum values, persisted through afternoon despite repair attempts, and gradually resolved during evening thermal recovery, suggesting that the primary causal factor was sustained cold exposure exceeding component thermal tolerance thresholds rather than any single point of system design or installation error.